All right. Hello, everyone. Happy to be here today to cover the basics of AI. So let's all start by just taking a deep breath. And the title of this talk refers to a novel by Douglas Adams, in which The Hitchhiker's Guide to the Galaxy is the reference book, because the cover says, "Don't panic" in large letters. And I've said this before in the past about measurement uncertainty, and now I'm saying it about AI. Don't panic. Over the past years at conferences, I've sensed a real sense of I have no idea what this person is doing, and I couldn't possibly question them about what they've just presented. And well, enough. Okay, this is not good for anyone. If AI's role in what we do is to grow, then we need to have some basic grasp on how it works. And so today I want to give you a basic proficiency in AI concepts, so you don't look like a deer in the headlights next time a talk mentions it. Right, we only have half an hour here, so let's rock and roll. Right, no better place to start than with a definition, right? What is AI exactly? Well, maybe unsurprisingly, given all the confusion that surrounds AI, there are lots of different definitions available. But we can use a basic one that works pretty well. Artificial intelligence can be defined as the process of building and using computer programs to simulate human intelligence. For example, in terms of pattern recognition or logical series of decisions. And it's everywhere in our modern life. Text to completion, voice recognition, picture to tagging, spam filtering, ad personalization. And what we gather from this list is not only is it everywhere, but also it's been there for a long time. We have the feeling that AI has just jumped at us, but no. I mean, spam filtering goes back to the 1990s, right? Well, this is a pretty large definition and it covers a lot of ground, but of course, we can break AI down into different categories. And there are several ways to do that, just like there are several ways to categorize drugs, right? We can look at their scheduling, their effects, their molecular property, and so on. Well, one of the ways we can categorize AI applications is by looking at the kind of task that they're accomplishing. So, narrow AI acts on a specific problem or task. That is what we typically see in forensic toxicology in terms of research projects. Generative AI uses training data to generate new outputs, and that can be text, video, or images on demand. Predictive AI aims to predict what will occur in the future. For example, which employees will perform poorly. General AI or AGI refers to an AI capable of performing any task better than a human. And finally, agentic AI is somewhat of a meta category. It can be all of the above, and it refers to autonomous AI systems pursuing multi step complex goals on their own. But I'm more of a under the hood, how the maths work kind of girl. And so let me present a classification which speaks to the mechanics of AI. Well, historically, there have been two main approaches to achieve AI. First, we have symbolic AI, including expert systems. These are kind of close to traditional rule based programming, and they rely on encoding human knowledge and reasoning explicitly in the computer. These were popular up until the 1990s. But the main star is now, no doubt, machine learning. Using a large data set, the computer program figures out by itself what the best parameters are to achieve the task at hand, right? In rule based programming, we would have to provide those parameters. Um, and in machine learning, the computer figures this out by itself. And a subcategory of machine learning are the famous neural networks. And a subcategory of neural networks is deep learning. But we can also split this categorization across another orthogonal dimension, the types of AI. And so, depending on the source, you will see between 2 to 5 of them cited. I'll cover three main ones today: supervised, unsupervised, and reinforcement learning. These things are easier with an example. And so let's say I want a machine learning algorithm to, hey, predict retention time of new NPSs, right? And well, in supervised learning, you have a data set with several variables. So for example, pK, molecular weight, number of halogens, number of and length of aliphatic chains, and so on. And I also have several observations for which all variables are measured. And so, for example, I could have a set of 100 NPSs for which all of the different variables are available. And these are paired with the expected output, the retention time. And so we say that these observations, they are labeled, and this is a labeled training set. So we have, hey, here's the information that I'm going to have on hand, and here's what you should spit out. And you give that to the machine learning algorithm, and it figures out by itself some kind of mathematical function. And once you have that, you can give it some never seen before input, right? It runs it through the mathematical function and it gives you a predicted output. In this case, the predicted retention time for this brand new NPS never seen before. And the outputs here, they can be numerical, like a retention time, or a postmortem interval in days, for example, or they can be categorical, like cause of death. So this is supervised learning. But you can also have unsupervised learning with an unlabeled data set, right? Just the inputs. And what you do is you just feed that to the machine learning algorithm and it just figures out what's interesting about this data set, which observations cluster together, and conversely, which observations are way out there and absolutely do not cluster with the others. Or you could also use this to shrink the number of variables without information loss. Pretty useful when you have large multivariables data set. The last type we'll cover is reinforcement learning. This is used in complex tasks with sequential decisions where the end goal is pretty clear, but the exact correct decision to take at each individual moment is not obvious. Training a robot to complete an obstacle course would be an example, right? You know that if the robot falls flat on its face, it's not a good outcome. But which way exactly should the robot put its foot? That's not so obvious to say. Well, reinforcement learning is like dog training, but for your computer model, really. So you start with a random model. If the outcome that you get is good for you, you go good model and you give it a treat like additional points. If you don't like the outcome, you go bad model and you penalize it by removing points. And the reinforcement algorithm aims to maximize the total rewards or the points, and with enough repetition, it will learn the best strategy. Okay, so at this stage, we sort of have a basic cartography of AI along several types of groupings. But the question remains, right? How does it work? So I'll try now to give you a broad intuition for this. So machine learning has four key components. First, we have an algorithm, which is a generic set of rules with which the problem can be solved. Um, it also has a loss function that is an equation to calculate the difference between the real output and the one that's predicted by the model. But that's for a single data point. And so you need a cost function, an equation summarizing the loss over all data points. And finally, you need an optimization routine, which is a method for minimizing the cost function, right? We want to have a model that gives a result as close as possible to the true value. And the final result is the model, an equation that will take any new input and yield a predicted output. All right, I'll use a great toy example to demonstrate how this unfolds, the linear regression. And for those of you wondering, wait a minute, that's not machine learning. We have equations to obtain the value of the regression parameters. Well, yes, linear regression does have what we called a closed form solution. But it turns out that when you have tens of thousands of variables, the machine learning version of it is faster to compute, right? In our calibration curve, we only have a couple of variables, so that's not an issue. But that's why the machine learning version of it exists. And also, it's a good demo, so we'll use this. All right, so let's say my goal is to predict the postmortem interval. I have one variable, the concentration of some endogenous molecule, and the output is the postmortem interval in days. And so my algorithm here is the generic form of the linear regression equation. That's how I want to solve this problem. So, okay, how do we get the computer to learn what the best equation is? Well, we start with the loss function, which remember looks as looks at the difference between the real output and the one predicted by the model for one data point only. And in our case, it would look something just like this, right? Distance between the model and the real point. Well, those of you familiar with the maths of regression might be thinking, that looks just like, well, yeah, a residual. For our purposes, though, we're just going to square it so we don't have to deal with the fact that some of them are negative and some of them are positive, and then the average is zero. So that is our loss equation. Y hat, the value predicted by the model, minus y, the true value, squared. But of course, we want a summary value for all data points, and that's what the cost function will give us. And this would be a cost function for the linear regression. Don't get fooled by all the mathematical operators here. Essentially, this is just the average of the loss for all of the points. And the key thing to realize here is that changing the model will change the cost. Well, let's say we're just changing the slope of the regression. Well, if we start with this very bad model for the data, we get a really high cost. Getting a better model will reduce the cost. And with what we can consider a good model, the cost will be low. And if we overshoot with the slope, then the cost is going to start rising again. And so we can build this graph of cost versus the parameter. And we see that we seek to minimize the cost. And this is an optimization problem. Well, the most common approach to optimization is called gradient descent. And it is akin to finding your way on the mountainside. So imagine you're plucked on a very foggy mountainside, say New Zealand, and you need to find your way back to the village at the bottom of the valley. Well, just by feeling the ground directly around you, you already know which way the slope is going and in which direction you should be taking your next steps if your goal is to go downhill. And so you go in that direction, maybe just one step or two, and then you reevaluate. Am I going in the right direction? Should I switch course? And back off you go until there's no more down to go because you've found the village. Well, that's pretty much what we do in machine learning as well. So we start somewhere on the cost function, and our goal is to reach the minimum. So we feel the ground, so to speak, using a derivative at that point, and we go in the downhill direction, and we rinse and repeat until we are at the bottom of the bowl, and the derivative is zero. Cool, eh? All right, I've simplified a thing or two, though, because it's not one but two parameters in the linear case that we need to adjust, right? The slope and the intercept. And so the cost function would be more of a bowl shape, just like this. Still, same optimization idea applies here. It's just that our derivative has two different variables. And so putting together each of our key elements, a linear regression is an algorithm, a loss function to see how far the model is from reality, a cost function to summarize that over all data points, and an optimization routine to find the minimum cost. Well, what you get is the optimal model, where machine learning has learned what the best parameters are. Well, as I said, this was a quite simple toy algorithm, but of course, many other algorithms exist. Logistic regression, rectify linear units, support vector machines to find the boundary between groups, decision trees and random forest, k-nearest neighbors, and so much more. All right, now that we have a basic understanding of how machine learning works, it will be much easier to understand the famous neural networks. So, in the simplest neural network, we have three layers. The features layer is the measurements you have that you want to feed to the model. And then we have the hidden layer, which contains several neurons. In this case, we have three neurons, right? Those yellow circles. And in each of these, there's a mathematical equation that is going to take as input all of the different measurements, the features. And this equation is called an activation function. And it can be several things. Common choices are logistic regression and rectified linear unit. And this equation, it spits out some number that then feeds into the final layer, the output layer. So the first neuron takes all the features, applies an equation, spits out a number. Same happens for the second neuron. Take all the features, apply a different equation, spit out a number. And again, same thing for the third neuron. And if we put all of that together, that's how we get this mess of a diagram for neural networks. So all neurons of the hidden layer, they take up as input all of the observations, they apply some equation, different equation for each neuron, and they spit out a number. The result for each neuron then gets fed to another equation in the output layer, which will yield the final answer. And the machine learning part in all of that is those equations in each neuron of the hidden and output layer, they don't come out of nowhere. The computer learns on its own what the best equation parameters are. And if you think that's a lot of parameters to optimize, well, you haven't seen anything. Because hey ho, we can have more than one hidden layer. And each of these can have way more than just three neurons. So that's a lot of optimization going on, right? And so when we talk about deep learning, that's what we're referring to. It's neural networks with more than one hidden layer. So neural networks, they're best suited to complex pattern recognition tasks where large amounts of data are available. Now, as you've no doubt have gathered, um, deep learning neural networks, they're quite important for modern AI. And I could talk about them for a while, but time is running, and I need to talk about the performance of AI tools. So, as forensic toxicologists, the idea that methods and tools must be validated, that they must demonstrate their fitness for purpose, is quite familiar to us, right? Well, the same is true of AI and machine learning tools. Their performance must be validated. And to do that, the very first thing that we do after data collection for a project is to split the data set into three parts. We've got about 75% of the data that goes into the training set, and this is what's used by the machine learning algorithm to train the model to learn the best parameters. About 15% goes into the validation set. Now, don't be confused. This is not what we call validation. The validation set is used to compare the performance of different machine learning algorithms or to fine tune some parameters that need to be set by the human. And the final 15% is what we would instinctively call validation. It's the test set. And this is the data that's used for the final evaluation of the model's performance. Well, what you don't do, right, is feed all of the data to the algorithm and go, how does the final model perform on this data? No, that would be like evaluating the bias of a method by looking at how far the quantification of standards is from the true value. That gives you an optimistic view, right? These standards, they contributed to establishing the equation in the first place, so they will perform better, right? What you do is you keep an untouched data set or quality controls that didn't contribute to the model. And same goes for AI. Test set is your quality control for your AI process. Okay, how we measure performance will be extremely dependent on the project. When the output is a number, we can look at measures of accuracy. For example, we're pretty used to this, right? In some cases, the output is going to be somewhat fuzzy and hard to describe in terms of success and failure. One example of this would be the description of pictures. Is not including an element of failure, which elements are important, not important to include. In this type of situation, you need to think really deeply about how to define performance. But one other very common type of output is a category. So, for example, cause of death, present or absent. In this type of situation, you can use common categorical performance metrics. And there are a lot of these. Precision, accuracy, recall, F1 score, um, receiver operating characteristic curves area, or ROC AUC, are some of the most popular. We don't have time here to go through each of these equations, right, and how to calculate those. But essentially, they're all based on the number of true positives and true negatives, number of false positives or false negatives, or essentially misclassifications and correct classifications. And all of these are just rearranged differently for these different equations. Um, and if there are so many metrics, it's because they each serve different purposes and they're useful in different situations. So you need to be mindful in picking the one that you will use. And so, for example, using accuracy as a metric when you have class imbalance is a bad idea. Class imbalance is when you have one outcome, for example, patient has uber rare cancer, which is so much less likely than the other patient does not have this type of cancer. In this case, the problem is the model can completely ignore the problem at hand, just shove everyone into the not cancer category, and still pass accuracy with flying colors. For example, with a still pretty high prevalence of 5%, obtaining zero true positives for the disease will still yield 95% accuracy. Not good. A poor performance of the model generally indicates that there is an issue with how well the model fits the data. The model might be underfitting the data, right? For example, we have this linear regression up top where a quadratic one is clearly warranted. This is also called high bias in the machine learning world. And this might happen because the model is too simple. Again, maybe you need a quadratic instead of a linear regression. Or it might be because your features are not informative enough. Try as you may, height and weight will never give you cause of death. That's not relevant information. And to solve this, you could, for example, increase the number of features. That's not the only option, though, but we haven't really covered the technical ground to understand the other one, so I'll just leave it there. You can also have overfitting, also called high variance. This happens when the model fits the training data too well. It has learned all of the data's idiosyncrasies, but it fails to generalize to new, previously unseen data. And this might be because the model is too complex. Instead of having whatever this top model is, you really should be having a quadratic regression, right? It might also be the case that you don't have enough data, or you might have too many features. And so you might have guessed just from the causes listed, but solutions would be to decrease the number of features or collect more data. When you have good model performance, you're in the Goldilocks zone. The fit is just right, it works for the training data, and it generalizes well to previously unseen data. Well, that's what we want, of course. All right. Well, I hope this talk was useful to some of you. At least now you have a definition, several ways to categorize AI using its purpose, knowing that deep learning and neural networks are subcategories of AI, knowing about supervised, unsupervised reinforcement learning, and you also have a basic understanding of how it learns using the algorithm, the loss and cost function, the optimization routine, and you know that you need to evaluate performance and how to do it. And hopefully, this will allow you to understand more of the AI talks at your next conference and ask better questions from the speakers. There are tons of interesting stuff I couldn't cover today because of the limited time. If you're interested in digging deeper, still in a very conversational, approachable, understandable manner, I have a piece coming out in the next few weeks in the TF Bulletin, which is essentially an expanded version of this talk. And for those of you who would like to dig even deeper in the maths, these are my recommendations. Why Machines Learn, which is a really nice piece of vulgarization, not a technical manual, and the 100 pages machine learning book, which is a bit more mathy and technical, but not overly so, and really brief. Plus, you can view it for free online to see if that's your jam. Another thing we haven't covered in this talk is, okay, well, given how AI works, what can we say about its adequate uses? How can we use it in a way that's in line with its technical limitations? And this book here talks about this very topic across all kinds of different domains. And recently, Tyler DaVincenzi and myself submitted a letter to the editor in the Journal of Analytical Toxicology, and it's still under review, but an expanded version of it is available right now as a preprint on ResearchGate if you would like to read it. Of course, it focuses specifically on forensic toxicology considerations. Okay, well, if you have any questions, comments, requests for papers, I mean, feel free to reach out. I've put my email up there, but it appears we're the latest victim of our leader's favorite pastime, changing the name of ministries, and so this email might not be working for long, in which case I'm easy enough to find online anyways, on LinkedIn, for example.